Somewhere, in a quiet field in northern Europe, there is a boulder that does not belong. It sits alone in the soft grass, taller than a person, a great lump of gray stone, and if you were to chip a piece from it and carry it to a geologist, they would tell you something strange. This rock is the wrong kind of rock for this place. It matches no outcrop for hundreds of kilometers around. Its nearest relatives are far away, in mountains it could never have rolled to on its own. And yet here it rests, in the middle of a gentle lowland, as if something enormous had picked it up, carried it across the land, and set it down here, very gently, a long time ago. For most of human history, nobody could explain stones like this one. They turned up all over the northern world, scattered across fields and forests, sitting on hilltops, lying in valleys, always made of rock that came from somewhere else. People gave them names and stories. Some thought a great flood had floated them here. Some thought giants had thrown them. They became boundary markers and altars and places where you left an offering, because a stone that had clearly traveled, that had no business being where it was, felt like it must mean something. It did mean something, but the answer was so vast, so far outside anything people expected, that it took more than a century to believe. The boulder had been carried by ice, not a passing winter's ice, but a sheet of ice taller than a mountain, that once lay across the whole of the north and slowly, over thousands of years, ground its way southward, dragging stones in its frozen belly and dropping them where it finally melted. That field where the boulder rests was, not so very long ago, buried beneath ice you could not see the top of. And tonight, I'd like to tell you the long, slow story of that ice, where it came from, where it went, and how a handful of patient people, working across 2 centuries, finally worked out the rhythm that freezes a world and then sets it free again. There's nothing for you to do but rest and listen. Let the room go quiet, let your breathing slow, and let's go back to a colder Earth. Begin a little under 20,000 years ago, at the coldest depth of the most recent freeze. If you had stood on the land that is now Canada or the northern United States, you would not have recognized the world at all. There were no cities, no forests, no open green country. There was ice and only ice, stretching from horizon to horizon, white and gray and faintly blue, rising in places to nearly 2 miles thick. Beneath that ice lay the ground where Toronto and Chicago and Montreal would one day stand, pressed down flat and dark under a weight almost beyond imagining. A great dome of frozen water, the Laurentide ice sheet, sat over the whole top of the continent, and a second one, the Fennoscandian, lay across Scandinavia and Finland and reached down into the plains of what is now Germany and Poland. The weight of that ice did something quietly astonishing. It was so heavy that it pushed the solid crust of the earth downward, sinking the land into the soft, yielding rock of the mantle beneath, the way a person sinks into a thick mattress. And when at last the ice melted away, the land did not spring back at once. It began, very slowly, to rise. It is rising still. In parts of Canada and Scandinavia, the ground lifts by a small fraction of a centimeter each year, even now, a faint and patient recovery from a burden that vanished more than 15,000 years ago. The land remembers the ice long after the ice is gone. So much water was locked up in those frozen sheets that the seas of the world ran low. The oceans stood roughly 120 meters beneath their present level, 400 feet lower, and where the water drew back, it left dry land that no longer exists. Britain was not an island then. It was joined to mainland Europe by a broad, low plain we now call Doggerland, a country of rivers and marshes and gentle hills where people hunted and fished and lived their whole lives. There was no English Channel, no North Sea as we know it. You could have walked from the place that is now England to the place that is now France without once getting your feet wet. And then, As the ice melted and the seas rose, Doggerland slowly drowned. The water crept in over thousands of years, swallowing the hills, turning them into shoals and then into open sea, until Britain was cut off and became an island. An entire inhabited land simply went under, and the people who had lived there moved on, and in time forgot it had ever been there at all. On the far side of the world, the same drop in sea level opened a different door. Where the cold strait between Siberia and Alaska now lies, there was then a wide grassland bridge, 1,000 kilometers across, joining Asia to the Americas. This was Beringia, and across it, sometime in the long cold, the first people walked into a continent that had never known a human footprint. Following the herds, drifting east and south generation by generation into a new and empty world. 2 continents joined by dry land, and the whole later history of the Americas resting on the fact that, for a while, the sea had simply gone somewhere else. The cold was not, on average, as deep as you might think. The whole planet was perhaps 5 or 6 degrees colder than it is today, which sounds almost mild. But an average hides the truth of it. The poles were colder by 10 or 15 degrees, the tropics only a little cooler, and that uneven chill was enough to remake the surface of the earth. Forests gave way to tundra and open grass. A vast, cold, dry plain, the Mammoth Steppe, ran unbroken from Western Europe across the whole of Asia and over the land bridge into North America, the largest single landscape the world has known, and it teemed with great, shaggy animals built for the cold. Woolly mammoths and woolly rhinos, ground sloths as big as small cars, cave bears, the great saber-toothed cats, and the long-legged dire wolves. They wore thick coats and carried their fat through winters that lasted most of the year, and they moved across that frozen grassland in their millions. People were there among them. Our own kind, in Europe and Asia and Africa, wrapped in skins and gathered around fires, sheltering through the long winters and hunting the great animals when they could. And we were not alone. The Neanderthals were still in Europe then, a people whose ancestors had endured the cold far longer than our own, stocky and strong and deeply adapted to it, with broad chests and wide noses that warmed the frozen air before it reached their lungs. They were survivors in the truest sense. But their numbers were thinning, worn down by the slow pressure of a changing world and by sharing it with us. And within a few more millennia, they would be gone entirely, leaving only their bones and a faint trace of themselves still carried, even now, in the blood of nearly everyone alive outside Africa. We remained. We would outlast the ice, and when it melted, we would inherit the warmth. And the world was not only cold, but dry. Locking so much water up as ice took it out of the great cycle of evaporation and rain, so the air carried less moisture and less fell from it. Deserts grew. The Sahara spread wider than it is now. The rainforests shrank back and broke into patches, the Amazon reduced to islands of trees in a sea of grass. With less green to hold the ground down, the wind lifted the bare soil into the sky, and dust traveled across whole continents and settled in thick, pale blankets that we still find today. Layers of wind-blown silt many meters deep across China and Central Europe and the plains of North America. A quiet record of a world that was, for a long time, brown and windy and bitterly cold. That is the world the boulder remembers. That is what lay over the field before the grass returned. And the deepest question, the one that would take 100 years and 4 different sciences to answer, is simply this. What brings such a world into being, and what, after tens of thousands of years, finally melts it away? The first part, simply believing the ice had ever been there, was harder than it sounds. The traveled boulders were only one clue among many, and for a long time the clues were read wrongly. On bare rock in the valleys of the Alps and across the lowlands of the north, Careful eyes began to notice long, parallel grooves cut into the solid stone, all running the same way, as though some immense tool had been dragged across the country in a single direction. Water does not carve stone like that. Wind certainly does not. But a glacier does. As a river of ice creeps forward, it carries broken rock frozen into its underside, and those embedded stones scratch the bedrock below like teeth on a file, leaving scratches that point exactly the way the ice was moving. Map enough of those scratches, and you can draw the lost flow of a vanished glacier, and the map kept showing the same impossible thing. Ice had once reached far, far beyond any glacier alive today. There were other marks. Long ridges of jumbled rubble snaked across the landscape, heaps of rock and gravel and sand bulldozed up and abandoned, exactly the kind of debris that ice piles at its edges and leaves behind when it withdraws. And there were the valleys themselves. A river, cutting down through rock over ages, carves a narrow notch with a sharp bottom, the shape of the letter V. A glacier carves quite differently because it fills the whole valley and grinds against both walls at once, leaving a broad, smooth trough with a flat floor and steep sides, the shape of the letter U. These wide, gentle valleys lie all through mountains that hold no ice at all today, silent molds left behind by glaciers that melted long ago. For a long while, the learned world refused to read any of it as ice. The fashionable explanation was a great flood, the biblical deluge, perhaps, that had swept across the land and dropped the boulders and scoured the rock. Floating icebergs, broken from some northern sea and drifting over the drowned country, were called upon to explain the traveled stones. It was a tidy idea, and it was wrong, and it held the field for decades simply because the alternative was too strange to swallow. The man who finally broke it open was a Swiss naturalist named Louis Agassiz, born at the very end of the 1700s. He had made his name studying fish and their fossils, but he lived among the Alps, and the Alps have glaciers, and Agassiz began to look at them with new attention. He saw that the rock around the living glaciers bore exactly the marks found in the distant lowlands, the same scratches, the same ridges of debris, the same stranded boulders. And he made the leap that others had flinched from. If these glaciers had carved such marks, and these same marks lay scattered across half a continent, then the glaciers must once have been vastly larger. Ice must once have buried not just the high valleys, but the plains and the cities to be, whole countries of it, in an age he named with two plain words: the Ice Age. He announced it in 1837 to a room of fellow scientists, and they did not thank him for it. The idea seemed wild beyond reason, that the gentle green country around them had so recently lain crushed under a mile of ice. He was doubted, dismissed, quietly mocked. But Agassiz was stubborn in the patient way that wins arguments in the end. He gathered more evidence, walked more valleys, wrote and argued and persuaded, and slowly, across a generation, the doubt wore away. By the closing years of that century, the thing was simply accepted. The earth had been deeply, repeatedly cold. There had not been one ice age, but several, great freezes separated by warmer spells, written plainly in the rock for anyone willing to read it. And that only deepened the mystery, because now there was a far harder question waiting. Knowing that the ice had come and gone, again and again, the obvious thing to ask was why. What could reach out and chill an entire planet, hold it frozen for ages, and then release it, on a schedule regular enough to repeat? The first guesses were reasonable and mostly wrong. Some supposed the sun itself dimmed and brightened, cooling the earth when its fire sank low. But there was no sign of it, and no clock to set it by. Some blamed the volcanoes, whose great eruptions can veil the sky in ash and chill the world. And it is true that a large eruption can cool the climate, but only for a year or two or three, nothing remotely long enough to grow a continent of ice. Others looked to the ocean's currents, or to the slow rise of mountain ranges, and each of these, it would turn out, played a part. But none of them was the heart of the matter, and none could explain the one feature that mattered most: the rhythm. The ice did not come at random. It kept time. And to find what kept that time, you had to stop looking at the Earth and look instead at the sky. A few people had already begun to suspect as much, long before the answer was proven. In the 1840s, a Frenchman named Joseph Adamar suggested that the slow wobble of the Earth's axis might govern the freezes, the first to tie the ice to the motions of the heavens. His particular idea was flawed, but the instinct was sound. A generation later, a far more remarkable figure took it further. James Kroll was a Scotsman with almost no formal schooling, a man who had worked as a tea merchant and an insurance salesman, and at last as a humble caretaker, a janitor, in a museum in Glasgow. Surrounded by its library, in hours stolen from his sweeping, he taught himself the mathematics of the heavens and built a real theory of the ice ages, one that drew on the shape of the Earth's orbit and the tilt and wobble of its axis together. His work was taken seriously by the great scientists of his day, an extraordinary thing for a self-taught caretaker, and though parts of it were later overturned, he had seen the true shape of the answer decades early. The full solution, the one that would finally fit the evidence exactly, was still to come. And it would be calculated, astonishingly, by hand, by one patient man working alone for the better part of a lifetime. His name was Milutin Milankovic, a Serbian engineer and mathematician working in the early years of the 20th century. He understood something that Kroll had glimpsed, that the Earth does not move around the sun in a fixed and unchanging way. Our path and our posture shift, slowly, over thousands of years, nudged by the gravity of the other planets. And Milankovic believed that those gentle shifts decided how much sunlight fell on the far north, and that the far north was where ice ages were won or lost. So he set out to prove it the only way available to a man of his time, with paper and pen and patience, working out the precise position of the Earth and the precise strength of the sunlight at chosen latitudes, for moment after moment, stretching back across hundreds of thousands of years. It was slow, grinding, almost unimaginable labor, and he gave it the better part of 3 decades of his life. What he was tracking were 3 separate slow rhythms, 3 ways the Earth's relationship to the sun keeps quietly changing. The first is the shape of our orbit. We tend to picture the Earth circling the sun in a neat ring, but the path is really an ellipse, a gently stretched circle, and the amount of stretch is not constant. Over a span of roughly 100,000 years, the orbit swells from nearly round to a little more oval and back again, breathing in and out under the steady gravitational pull of the giant planets, Jupiter and Saturn above all. Today, the orbit is very nearly circular and growing rounder still. When the orbit is more stretched, the Earth's distance from the sun varies more across the year, and the sunlight it receives varies with it. When the orbit is round, as now, the year is more even. This is the longest of the 3 rhythms, and it would turn out to hold a stubborn secret of its own. The second rhythm is the tilt of the Earth itself. Our world does not spin upright, it leans, at present by about 23.5 degrees, and that lean is the reason we have seasons at all. But the angle of the lean is not fixed either. It rocks slowly back and forth between roughly 22 and 24.5 degrees over a cycle of about 41,000 years. And the tilt matters enormously because it sets how fierce the seasons are. When the Earth leans harder, summers grow hotter and winters colder, the poles tipping more boldly toward the sun and then away. When the lean is gentler, the seasons soften, milder summers, milder winters. Here is the quiet hinge on which an ice age turns, and it is not what most people would guess. Ice does not build up because winters are cold. Winters are always cold enough to snow. Ice builds up when summers are cool, cool enough that the snow which fell in winter does not entirely melt away before the next winter buries it deeper. Year after year, the unmelted snow stacks up, hardens, and becomes ice. So it is the gentle, weak-summered phases of the tilt that let the ice grow, and the strong-summered phases that strip it away. There is something worth pausing on here, because the very steadiness of that tilt is a gift. The angle of the Earth's lean is held in its narrow, well-behaved range by the steadying pull of the moon. Were the moon not there, our tilt would lurch about wildly and unpredictably over time, swinging through huge angles, and our seasons and our climate would heave from one chaos to the next. The same moon that draws the tides and lights the night also keeps the Earth's posture calm, and in doing so, it makes our ice ages gentle and rhythmic rather than violent and random. We owe the very regularity of these great freezes in part to the quiet companion in our sky. The third rhythm is a slow wobble. A spinning top, as it slows, does not just spin, its axis traces a lazy circle in the air. The Earth does the same, far more slowly, its axis sweeping out a full circle over some 26,000 years. This wobble does not change the tilt, but it changes the timing of the seasons against the shape of the orbit. Which hemisphere happens to be leaning sunward at the moment the Earth is nearest the Sun, and which is leaning sunward when it is farthest. At present, the northern half of the world has its summer when the Earth is at its most distant from the Sun, which makes northern summers a little gentler and cooler, exactly the kind of mild summer that favors the building of ice. 13,000 years ago, it was the other way round, and 13,000 years from now, it will swing back again. Tangled together with the stretch of the orbit, this wobble produces beats of roughly 19 and 23,000 years, and these too leave their mark on the ice. Milankovitch wove all three rhythms together and asked a single, focused question. Across the long past, how much summer sunlight reached the latitudes near 65 degrees north, the latitude of northern Canada and Scandinavia, the very cradle where the great ice sheets are born? Pile up enough cool summers there, and the ice should grow. Bring a run of warm ones, and it should melt. And when he plotted the answer across the ages, the cool summer phases and the warm summer phases fell, again and again, close to the times the geologists had marked for ice and for thaw. The orbital arithmetic and the buried evidence seemed to be telling the same story. He set it all down at last in a great and detailed book, a lifetime's calculation bound between covers. And the world, for the most part, shrugged. It was rigorous, it was beautiful, and it was largely ignored, because for all his mathematics he had no independent proof, nothing from the rock or the sea to show that the ice had truly kept the time his orbits predicted. He had a theory and a mountain of sums, and no way to test them against the Earth itself. Milankovitch died in the late 1950s, an old man who believed his life's work had been quietly set aside. He was wrong about that. The proof was coming. It would arrive within 20 years of his death, and it would come from the last place anyone thought to look for a record of the ice, the soft mud at the bottom of the deep ocean. In the 1960s, ships went out over the deepest water carrying drilling rigs, and they did something that would have seemed like fantasy a lifetime earlier. Holding their position over miles of open ocean, they lowered a drill through all that water to the seabed below and bored down into the mud, pulling up long, slender cylinders of sediment, cores, each one a stack of mud laid down grain by grain over millions of years, the oldest layers at the bottom, the youngest at the top. An unbroken diary of the sea, if only you knew how to read it. And the writing, it turned out, was in the shells of creatures almost too small to see. The deep mud is full of the remains of tiny, single-celled drifters called foraminifera, plankton that built themselves delicate shells of chalk while they lived in the sunlit water above. When they died, by the countless billion, their shells sank and settled into the growing mud, and locked inside the chemistry of each little shell is a faint print of the world it grew up in. How warm the water was, and, most precious of all, how much of the planet's water was at that moment locked away as ice. The key to reading it lies in oxygen, and in the fact that not all oxygen weighs the same. Almost all the oxygen in the world is of one light, ordinary kind. But a tiny fraction of it is a heavier version, carrying a little extra weight in each atom. And that small difference in heaviness has a quiet consequence. When water evaporates from the warm surface of the sea, the lighter water lifts off just a touch more easily. So the vapor that rises into the sky is slightly richer in light oxygen and slightly poorer in heavy. That vapor drifts to the cold places and falls as snow, and during an ice age, that snow piles up on the growing ice sheets and stays there, held fast for age upon frozen age. So as the ice grows, it hoards the world's light oxygen, and the ocean left behind grows ever so slightly richer in the heavy kind. The little shells forming in that ocean take up the balance exactly as it is. And so each shell becomes a tiny gauge, reading high and heavy oxygen when the ice is vast, and low when the ice has melted back into the sea. Measure that balance, shell by shell, layer by layer down a core, and the rise and fall of the world's ice is laid out before you like a tide chart of the ages. An Italian-born scientist named Cesare Emiliani was the first to truly work this magic in the 1950s. He measured the heavy oxygen signature in shells drawn from deep-sea mud and watched it swing up and down in a long, repeating procession of peaks and troughs, cold spells and warm spells marching back through time. He sorted them into numbered stages, giving the warm interludes the odd numbers and the cold glacial depths the even ones, a tidy ledger of the climate that scientists still use today. He could see the rhythm plainly. What he could not yet do was prove what set its beat. That last step fell to 3 scientists in the 1970s, working with longer cores, sharper dating, and finer measurement than Emiliani had ever had. They took mud reaching back across the last several 100,000 years and read its heavy oxygen record in fine detail. And then they did something clever. They handed the wavering line of climate to a piece of mathematics designed to find hidden rhythms buried inside a tangle of data. The kind of analysis that can listen to a chord of music and name the separate notes folded inside it. They asked it, in effect, to listen to the long song of the ice and tell them which steady beats were hiding in it. And the answer came back clean and unmistakable. The record was ringing with exactly the rhythms Milankovitch had calculated by hand decades before. A slow beat near 100,000 years, another near 41,000, and faster beats around 23 and 19,000. The stretch of the orbit, the rock of the tilt, the wobble of the axis, every one of them was there, written into the mud of the seafloor, keeping the very time the orbits had foretold. The match was not vague or hopeful. It was precise, and it was overwhelming. The ice ages were not accidents. They were paced, set ticking by the slow machinery of the heavens. The result was published in the mid-1970s under a title that said everything in a single phrase, that variations in the Earth's orbit were the pacemaker of the ice ages, and it remains one of the most important things ever written about the planet's climate. It proved Milankovitch right, 18 years after he had died believing himself forgotten. A man who had spent his life filling page after page with sums in a quiet study had, it turned out, heard the heartbeat of the Earth before anyone could show him it was real. The ice came and went by clockwork, an astronomical clock so reliable that you could, in principle, run it forward or backward and calculate the freezes of the deep past and the deep future alike. It was a triumph, and it raised a new and harder puzzle in the very moment of its solving. For the orbital rhythms, real as they were were also surprisingly faint. The changes they make to the sunlight falling on the north are not large, a few percent, perhaps as much as a tenth in the strongest cases. And a few percent of sunlight by itself is nowhere near enough to bury Toronto under a mile of ice. The clock could explain the timing of the freezes beautifully. It could not, on its own, explain their depth. Something on the Earth itself had to be seizing that small nudge from the sky and magnifying it over and over into something enormous. To finish the story, the searchers had to turn from the orbits in the heavens to the feedbacks in the world, the great amplifiers that take a whisper of change and turn it into an ice age. The simplest of them is a matter of color. A dark surface, open water, bare soil, a forest, drinks in sunlight and warms. A bright surface, fresh snow, clean ice, throws most of it straight back into space and stays cold. So picture what happens when a little extra ice forms in a cooling world. That new ice is pale and mirror bright, and it reflects away sunlight the dark ground used to absorb, which cools the place further, which lets still more ice form, which reflects away still more light. Each step deepens the next. A small chill, once it begins, can feed on itself and run downhill into a deep freeze. And the same trap works in reverse. Let a little ice melt, bearing the dark land and sea beneath, and the newly uncovered ground soaks up sunlight, warms, and melts more ice in its turn. This single feedback, the runaway of bright ice and dark earth, can take a faint nudge and drive it in either direction toward an extreme. But color is only half of it. The other great amplifier is a gas, and to read its history, we needed a second kind of frozen archive. Not the mud of the sea this time, but the ice itself. When snow settles on a great ice sheet and is slowly buried and squeezed into solid ice, it traps tiny bubbles of air between its grains. Each bubble is a genuine mouthful of ancient sky, sealed away and kept for as long as the ice survives. Drill down through the ice of Antarctica or Greenland, pull up a core, crush the trapped bubbles, and you can breathe in a sense, the very air of 100,000 years ago, and measure exactly what was in it. The deepest of these ice cores, drawn from the high Antarctic plateau, carry a continuous record of the atmosphere reaching back some 800,000 years, layer after annual layer of frozen weather. And what the bubbles show is striking. Through every glacial depth, the amount of carbon dioxide in the air sank low, to around 180 parts in every million. Through every warm interglacial, it rose to around 280. That is a swing of roughly half again, up and down, ice age after ice age, and the temperature of the world rose and fell in lockstep with it, so tightly that the two lines might almost be tracing each other. Low gas, cold world. High gas, warm world. Again and again, without fail. Which raises a delicate question. Did the gas drive the temperature, or the temperature the gas? The finest ice records hold the answer, and it is subtle. In the great warmings, the temperature begins to climb first, and the carbon dioxide follows a few centuries behind. So the orbits and their faint sunlight start the change. They give the world a small initial nudge of warmth, but that first warmth shakes carbon dioxide loose. And once the gas begins to rise, it traps more heat, which warms the world further, which frees more gas still. The carbon dioxide is not the spark, it is the bellows. It takes the tiny breath of the orbital clock and blows it into a roaring fire. Without that gas feedback, the ice ages would have been faint, barely worth the name. With it, they became the vast, world-remaking events we find in the rock. So where is all that gas born? And where does it vanish to? Mostly into the sea. The ocean holds an immense store of carbon, many times more than the whole of the atmosphere, and the two are forever trading it back and forth, seeking balance. Cold water can hold more dissolved gas than warm, You have seen this yourself in a glass of soda going flat as it warms. So as the oceans cool in a glacial world, they draw carbon dioxide down out of the air and lock it away. The deep, slow circulation that turns the ocean over, carrying surface water down into the lightless depths and back, shifts and changes through an ice age. And in the cold times it tends to seal carbon away in the deep, far from contact with the sky, so that the air above grows thin in the gas. When the world warms again, that buried breath rises back to the surface and is exhaled into the atmosphere. The ocean, across the long ages, is quietly breathing, drawing the gas in as the ice grows, letting it back out as the ice retreats. And there is one more amplifier, and it is the most surprising, because it ties the freeze to the dust we met at the very start. Life plays a part. The sunlit surface of the sea is full of microscopic plants, drifting algae that take in carbon dioxide as they grow, and, when they die, sink and carry that carbon down into the deep. The busier this living rain, the more carbon is pumped out of the air and into the abyss. But in much of the open ocean, these tiny plants are starved, not for the usual nutrients, but for iron, which they need in the smallest traces and almost never get. And here, the dusty Ice Age world does something remarkable. All that wind-blown dust we spoke of, lifted from the dry and barren land, is faintly rich in iron. And as it drifts out over the sea and settles, it fertilizes the hungry plankton. They bloom, they grow, they die and sink, and they draw still more carbon down out of the sky. A scientist who studied this once said, only half in jest, that give him a shipload of iron and he could begin an ice age. And there was real truth hiding in the joke. The dust of a frozen world helps to feed the very process that keeps it frozen. Lay all of this together, and the picture finally comes clear. The orbits set the timing with their faint, patient nudge. The brightness of ice, the breath of the ocean, the bloom of iron-fed life, and the warmth-trapping gas all seize that nudge and multiply it, each feeding the others, a cascade of amplifiers that turns a few percent of stray sunlight into a continent of ice or its melting. It is a system exquisitely balanced and exquisitely sensitive, and it has been running this way, freeze and thaw, for millions of years. And yet, just as it seemed solved, the system kept one more riddle in reserve, and it is a strange one. For the last million years or so, the freezes have marched to the slow 100,000-year beat, long glacials of 80 or 90,000 years, broken by short warm spells of 10 or 15,000, then back to the ice. That beat matches the stretch of the orbit, the eccentricity cycle. But the stretch of the orbit is the weakest of the three rhythms. It barely changes the sunlight at all on its own. The tilt and the wobble shake the northern sunlight far harder. So why does the world dance most strongly to the faintest drum? Why is the deepest, most dominant rhythm the one driven by the gentlest push? The answer lies in the sheer ponderousness of ice. An ice sheet is not a thin film that brightens and dims with each flicker of sunlight. It is a mountain of frozen water, and it has weight and memory and momentum. Once it begins to grow, it tends to keep growing, because its own height lifts its surface into colder air and gathers more snow, and its brightness chills the land around it. And it is so heavy that it presses the very crust of the earth down into the soft rock beneath. And when at last it melts, the ground takes tens of thousands of years to rise back up. All of this gives the ice a deep, slow lag, a reluctance to answer the sky at once. It builds, grudgingly, across many cycles of tilt and wobble, ignoring the smaller pushes, until the conditions line up just so, and then it collapses, fast. 90,000 years to raise the ice, perhaps 10 to melt it away. That lopsidedness, that slow gathering and sudden release, is what stretches the rhythm out to 100,000 years. The ice sheet is like a great pendulum, pushed by several rhythms at once, but swinging by its own ponderous nature near a beat of 100,000 years. And so it rings most loudly there, magnifying the weak stretch of the orbit far beyond its true strength. What makes this stranger still is that the 100,000-year beat is, in the long view, a recent habit. Go back beyond about 900,000 years, and the ice kept a different time entirely. The older freezes were milder and quicker, marching to the 41,000-year rhythm of the tilt. Tilt sharpens, summers strengthen, the ice melts. Tilt softens, summers weaken, the ice creeps back. Simple, direct, modest. And then, around 900,000 years ago, the whole system changed gears. The freezes grew longer, deeper, more savage, and the beat slowed to the 100,000 years we live with now. Why it shifted, no one is quite certain. Perhaps the slow, age-long drift of carbon dioxide had sunk past some hidden threshold that made the world more sensitive. Perhaps the ice sheets had simply grown thick and broad enough to take on that ponderous, lagging behavior. Perhaps the loose soil beneath them had been scraped away by earlier glaciers, leaving the ice gripping bare rock in a way that changed how it moved. It is still argued over, but the change is plainly there in the mud and the ice, a turning point in the planet's mood, and we have lived in the new mode ever since. It would be easy, hearing all this talk of slow orbits and ponderous ice, to picture the freezes and thaws as gentle things, sliding into the cold and back out of it over many smooth millennia. For the most part they were. But the ice holds a quieter, more unsettling secret, one the Greenland cores revealed only when they were read in the finest detail. That within the long ice ages, the climate could also lurch. Again and again the records show the far north leaping warmer by a great many degrees within the span of a single human life, perhaps within a few decades, holding there for a while, then sliding back. Dozens of these abrupt jolts came and went through the last ice age, sudden swings that no slow orbit could explain, the climate flickering like a candle in a draught. Some of them seem tied to the ice itself losing its grip. Every so often, it appears, a great swollen lobe of the North American ice sheet would grow unstable and break apart at its seaward edge, launching a vast armada of icebergs out into the Atlantic. As those bergs drifted and melted, they dropped the rock and grit frozen inside them onto the deep seafloor, and we find those scattered stones today in the ocean mud, far from any shore, marking the moment each fleet sailed and died. Each of these icy invasions chilled the surrounding sea and threw the climate of the whole region into disarray. The most famous lurch of all came right at the end, as the last ice age was finally releasing its hold. The world had been warming for thousands of years, the great sheets retreating, the forests creeping north, and then, around 12,500 years ago, the warming abruptly went into reverse. In a matter of decades, the North plunged back toward the depths of the cold and stayed there for more than 1,000 years, a brutal relapse just when the thaw had seemed unstoppable. The likely culprit is one of the most quietly dramatic events in the whole story. As the ice melted, it pooled into an enormous lake of fresh water along the southern edge of the North American ice sheet, held back by a dam of ice. And at some point, that dam failed, and the lake emptied, a flood almost beyond imagining, out into the North Atlantic all at once. That sudden flood of fresh, light water seems to have stalled the great current that carries tropical warmth up into the Northern Ocean, the slow conveyor that keeps the North far milder than it has any right to be. Choke that current with meltwater, and the heat stops arriving. The North goes cold, fast. For more than 1,000 years it held in that relapse. And then, just as abruptly, the conveyor seems to have caught again. The warmth came flooding back, and within a few decades, the world resumed its climb out of the ice. There were other shudders, too, in the long thaw. At one point, a great surge of meltwater raised the seas of the world by something like 20 meters in only a few centuries, drowning coastlines faster than any people living on them could have understood. This is the hidden lesson folded inside the grand, clockwork story of the orbits, that the climate does not only move slowly and predictably, it has thresholds, tipping points, places where a steady push suddenly produces a sudden jump. For most of the time, the great machine turns its slow, astronomical wheel, but now and then it stutters and lurches and reorganizes itself in a human lifetime rather than a geological age. The smooth curves drawn from the mud and the ice, seen up close, are full of these little cliffs. The planet, it turns out, can change its mind quickly when it chooses to. All of this, the orbits, the feedbacks, the lurching thaws, belongs to our own recent ice age, the long Pleistocene of the last few million years. But it would be a mistake to think the Earth has always behaved this way. Step back far enough, and the truth is almost the opposite. For most of its 4.5 billion years, our planet has had no permanent ice at all. The normal state of the Earth, across the great sweep of its history, is warm, a greenhouse world of high carbon dioxide, mild oceans, and ice-free poles. Through the long age of the dinosaurs, the poles were forested and temperate, and a creature could have walked from the tropics to the far south without ever meeting a glacier. Ice ages, in the deep view, are not the rule. They are rare interruptions, scattered hundreds of millions of years apart, brief, cold parentheses in a mostly warm story. And when you look at those rare deep freezes, you find something quietly profound about what it takes to chill a planet for an age, and how often life itself was the cause. The most recent of the ancient freezes, before our own, settled over the world around 350 million years ago, and lasted, on and off, across many tens of millions of years. Its ice lay across the great southern supercontinent, the joined land of what is now South America and Africa and Antarctica and Australia and India, all clustered together at the South Pole. And the reason for it was, of all things, trees. This was the age when forests first conquered the land, when tall plants spread across the continents in vast, steaming swamps. To stand up tall, those early trees had evolved a tough, woody substance to stiffen their trunks. And here is the strange part. Nothing on Earth had yet learned to rot it. The fungi and microbes that today break down dead wood had not appeared. So when those forests died, they did not decay. They simply fell and piled up and were buried, layer upon layer, century upon century, their carbon locked away in the ground instead of returning to the air. We burn that buried carbon today. We call it coal, and we named the whole age after it. As all that carbon was taken out of the sky and pressed into the earth, the warming gas in the atmosphere thinned, the world cooled, and the southern ice spread and held for an age, until, in time, the volcanoes and the shifting continents fed the gas back into the air, and the ice withdrew. Older still, around 450 million years ago, there was a shorter, sharper freeze, and it too seems to have been triggered by life. This was the moment, more or less, when plants first crept out of the water and onto bare stone. For before them, the land had been naked rock, no soil, no green at all. The earliest land plants spread across the continents and began, with their roots and their faint acids, to break down the rock they grew on, crumbling it into the first soils. And the breaking of rock quietly drinks carbon dioxide out of the air, binding it into new minerals and washing it away to the sea. As the young plants greened the continents, they pulled the warming gas down with them, and the world cooled, and ice formed at the southern pole for a span of millions of years before the balance tipped back toward warmth. It is a pattern worth holding on to. Twice over, the simple act of life spreading across the land, first plants, then forests, reached up and cooled the whole planet by tidying carbon out of the sky. The living world is not a passenger in the climate. It is one of the hands on the wheel. But the most extreme cold the Earth has ever known lies further back yet, between roughly 720 and 635 million years ago. And it is so severe it strains belief. The evidence says that in that distant time, the ice did not stop at the poles or at the temperate lands. It marched all the way to the equator, and the entire planet, every ocean, every shore, from pole to pole, froze over into a single white ball. We know it sounds impossible, but the rocks insist. Glacial deposits from that age turn up on every continent, and when their ancient latitudes are red from the faint magnetism frozen into them, many formed not in the cold high north or south, but at the tropics, at the warm waste of the world. There are stones in tropical seabeds of that age that could only have been dropped there by drifting icebergs. The whole Earth, it seems, became a frozen wasteland, a snowball Earth, with temperatures crashing far below anything in our own ice ages, and it stayed that way not for thousands of years, but for millions. How a planet freezes that completely, and how it ever thaws again, is a story of feedbacks run to their limit. The setup was a quirk of geography. The continents of that time were gathered near the equator, where the warm rains weather rock fastest and pull down carbon dioxide hardest. The gas thinned, the world cooled, ice began creeping down from the poles, and then the bright ice feedback we met earlier took the reins. Each band of new ice reflected away more sunlight, cooling the next band into being. Normally, this would stall somewhere in the middle latitudes because the tropics drink so much sun that ice cannot easily cross them. But that time, with the gas already low and perhaps a chance volcanic chill or two to push it along, the ice crossed the critical line. And once it passed a certain point, nothing could stop it. Within a geological eye blink, the runaway closed the whole world in ice. And here is the wonder of it. The very same frozenness that seemed permanent carried the seed of its own undoing. Even on a frozen planet, the volcanoes never stopped. Year upon year, age upon age, they kept breathing carbon dioxide into the sky. But now there was no warm rain falling on bare rock to weather it back out again, because all the rock and all the rain were locked in ice. So the gas simply built up, with nothing to remove it, climbing for millions of years to staggering, suffocating levels, hundreds of times what we breathe today. And eventually, even a world wrapped in mirror-bright ice could not throw off that much trapped heat. The ice at the equator began to soften and melt. The dark sea showed through. The warming ran away in reverse. And in a few thousand years, the planet swung from the deepest freeze imaginable to a searing greenhouse. The aftermath is written in thick layers of carbonate rock laid down all over the world in the sudden, violent warmth, the planet's hangover from drinking down all that gas. Life, somehow, endured it all, clinging on in warm refuges beneath the ice, and when the thaw finally came, it bloomed into the first large, complex creatures the world had ever seen. There may even have been an earlier freeze of the same kind, far back around 2 billion years ago, when oxygen first filled the air and destroyed the methane that had kept the young Earth warm. Out of all these deep freezes comes one simple, unifying truth. An ice age, of whatever depth, needs the warming gas to fall low and stay low for ages. And that only happens when the slow chemistry of weathering rock pulls carbon out of the sky faster than the volcanoes can put it back. Set the continents where the rock weathers fast, raise fresh mountains for the rain to gnaw at, quiet the volcanoes a little, and the gas drifts down, the world cools, and if there is land near a pole for snow to gather on, the ice can take hold. It is a planetary thermostat, slow and patient, made of stone and rain and fire, and for most of history it has held the world comfortably warm. Only now and then does it slip toward the cold. And the most recent time it slipped is the cold we still live inside today. For we are, in the long reckoning, still in an ice age, a cool chapter that began far more recently than the dinosaurs and has not yet ended. It opened around 34 million years ago, when the slow drift of the continents carried Antarctica to its lonely seat over the South Pole, and a great current rose up to circle it, walling it off from the warm waters of the world and letting the cold close in. Ice gathered on that southern land and has never since left it. Far to the north, the rising of new mountains gnawed by the rain helped draw the warming gas lower across the ages, until at last, only a few million years ago, the cold reached up into the northern half of the world as well, and the rhythmic freezes of our own time began. Since then the ice has come and gone perhaps 50 times over, advancing and retreating to the beat of the orbits, and the great glacial world we began with, the mammoths, the land bridges, the drowned plains, was only the most recent of those many turns. And it ended, as they all do, in a thaw. The ice drew back, the forests returned, the seas rose to drown Doggerland and refill the strait at Beringia, and into that gentle warmth our ancestors carried fire and language, and before long, the first fields and the first cities. We call this warm spell the Holocene. And it began a little under 12,000 years ago, and very nearly everything we think of as human history, every harvest, every story written down, every wall and road and song, has unfolded within its quiet warmth. It is worth remembering, on a still night like this one, how thin and recent and lucky that warmth is. Some of the great mammoths, it turns out, did not vanish at the end of the ice at all. A last small herd lived on a lonely island in the Arctic Ocean, until only about 4,000 years ago, which is to say that there were still living mammoths in the world when the first pyramids were already standing in Egypt. The Ice Age is not as far behind us as it feels. By the slow arithmetic of the orbits, our warm spell is, if anything, getting on in years. The interglacials of the past have tended to last 10 or 15,000 years, and ours is already nearly 12,000 old. The shape of the Earth's orbit and the angle of its tilt are drifting, very gradually, back toward the kind of arrangement that has let the ice grow before. And so, left entirely to itself, the great machine would, in time, begin another slow descent, snow lingering a little longer each summer in the far north, the next freeze gathering across tens of thousands of years to come. That is what the clock alone would do. Whether the world will actually follow it now is, for the first time in the whole long age of these freezes, no longer a question. The orbits settle by themselves. Because the level of that warming gas in the air, the bellows that drives the whole system, is no longer being set only by rock and ocean and volcano. But that is a story for another night, and not one to carry into sleep. For tonight, it is enough to rest in the strangeness and the calm of it. Somewhere out there, the field still holds its lonely boulder, set down so gently by ice that no longer exists, on ground that is still, by a hair's breadth each year, rising back toward the sky. The same slow rhythms that buried that field and then freed it are turning even now, unhurried, indifferent, patient beyond any human measure. The long stretch and round of the orbit, the steady rock of the tilt held calm by the moon, the deep breath of the ocean drawing the gas in and letting it out. None of it is in any hurry. None of it needs anything from you. The ice will gather again, or it will not. ages and ages from now, long after this night and everyone in it has been forgotten, and the great wheel will turn just the same. So let it turn without you. Let the mammoths drift back into the white distance. Let the ice sheets settle and melt and settle again somewhere far beyond the edge of sleep. You are lying on warm ground that was once buried under a mile of ice, and will perhaps be buried again, and is, for this brief and gentle while, green and quiet and yours. There is nothing to solve and nothing to hold. Feel how heavy and still you have become, how the long story narrows now to the warmth of where you are and the slow rise and fall of your own breathing. The cold is far away, only a tale told over the centuries. The night is warm and patient and kind. Let the great slow rhythms keep their watch over the world, and rest now, and sleep well, here in the long, warm pause between the ice and the ice. Good night.